Hi, my name is Alex Stockness. I will be presenting the Electrical Power System Phase 2 review presentation for the ORCASat project. Let's jump into it. Oh. No, there we go. Okay. So let's talk about the point of this presentation really quick before we dive into it. The point of this presentation is to make sure that we are going to design the right thing. Yeah, that's basically the point of it. We want to make sure that we have our requirements and we have a plan that makes sense moving forwards, so we don't waste a bunch of time in the critical design phase designing the wrong thing. We want to make sure that we have requirements set and they make sense before moving forwards. So the point of this presentation, we're going to focus on the design process and how we derive those requirements and what our plan kind of is for meeting those requirements, and not so much on the implementation that we're going to choose, except for critical areas where we need to discuss them at this point in time. And then kind of propose a plan for critical design phase. Like, what are some things that we should be aware of, and how those affect time, money, and personnel. Without going into, once again, too much critical detail, this is not a critical design review. This is a preliminary design review. So this is the high-level preliminary design phase goal. So what we did in conceptual development was we basically floated around between taking mission requirements, flowing those into a power budget, and then determining subsystem requirements, and then checking to see if those were feasible, and then tweaking mission requirements until we had subsystem requirements that were feasible. Preliminary design phase is all about taking that power budget and building prototypes that physically verify if the subsystem requirements are feasible. And once we've kind of flown through that a few times, then we finally have a nice list of subsystem requirements, which we are able to use to design the actual product. This presentation is going to follow the format of the EPS design process outlined in SMAD. I'm not going to reinvent the wheel here. We're going to start with identifying the requirements, select and size power source, select and size energy storage, identify power distribution management, identify power regulation control. We're going to focus on steps 2 and 5 because those are the most important, or 1, 2, and 5. We're going to kind of skim over 3 and 4 for the time being. Step 1, identify requirements. So our mission summary, this is the high level kind of characteristics of our mission. We're looking at 1.5 watts average, and we're looking at a 2U nanosatellite in ISS orbit. For the power consumption, we're first going to break this down to get the load profile. So the load profile is broken down further into modes. So we have nominal mode, payload mode, and safe mode. Each has its own different characteristic of power consumption. Nominal mode, as you can see, basically everything is on except for the payload. Payload mode, everything except for the RX and the TX and the GPS are on. So anything that have wireless communications, we're turning those off so they don't interfere with the payload measurements or readings. And then safe mode, the payload is off and the TX is off, but the ADCS, TT&C and everything else is on. The thing that's important to note here is that the RX is always on. It's at 100% duty cycle. We're always listening. We're not turning the RX off ever. That is kind of the point of safe mode. And the CDH MCU goes into an ultra low power saving mode. So basically it's just sleeping. It's not executing commands or anything like that. It's just waking up, gathering telemetry, going back to sleep, and then waiting for that receive interrupt to wake up, more or less. And then startup, which is what happens when the spacecraft turns on, what things are booting up and working. This is the summary. So the conclusion here is that we need about 1.2 watts or 1200 milliwatts on average in nominal mode. And then with a 20% margin, we need about 1.5 watts. And the duty cycle for everything here is nominal mode is what the spacecraft will be in most of the time. When we do operate the payload, it's very little. We're only operating the payload, at most a few minutes per day. So the duty cycle is extremely low. And in theory, we're never going to be in safe mode or startup, but we'll get into those details later. So with a margin of 20%, we need to be able to supply 1.5 watts on average. And then the orbit that we have for this is ISS orbit. Not much to talk about there. And the spacecraft configuration is just a 2U nanosatellite with static solar arrays. That's the big one. So we're not doing deployable solar arrays. We have to make it work with static arrays. We don't really have the time or the engineering expertise to make deployable solar arrays work. And this spacecraft is 3x stabilized and it's nadir pointing. So it's not sun tracking, it's not spinning around, it's stabilized on all 3 axes and it's nadir pointing. So let's select and size our power source. So our average power generated, or the requirement for the average power that we need to generate in the sun is 4.09 watts max. So this is kind of where we get into it, where we only need to generate 3.72 watts typical with a minimum of 2.34, but because we're power budgeting for the worst case, we need to make sure that the satellite works under all situations. We have to power budget for the worst case, which in this case it's 4.09 watts max. And because we have static solar arrays, we're not so much specifying the size of the solar arrays as we're specifying, okay, how many cells do we actually need on the static solar arrays? And if we need more than what we can possibly fit, then we have to look at reducing the power consumption instead of increasing the solar array area. So by doing so, we're using the AzureSpace 3G30A solar cell assemblies because they have the highest efficiency to cost ratio of any photovoltaic cell that we were able to get a quote for. So with these solar arrays, our X arrays are able to support 2.4 watts, our Y arrays are able to support 4.8 watts, and our Z array is able to support 5 watts peak. So it looks like we should be good. But what we did here is, so because we're power budgeting for the worst case, we don't actually need to simulate the spacecraft for an entire year of orbit and check for the worst case. We know what the worst case is. We wanted to simulate it for 1 year in orbit regardless, just to get that data and look at the data and make sure everything makes sense and make sure that we didn't, think of anything or forget anything about ISS orbit and just have that data and feel more confident in the numbers. The tool we used for this was Martin Meerman's Astro Training. So this is the results of the simulation. Not really much to talk about here. In red, we have the average power generated, and in purple, we have the orbit average power. As you can see, the power generated averaged over the orbit, which is orbit average power, is at the all-time high when we have no eclipse. So we're spending all the time in the sun. That makes sense. And then average power generated changes changes based off of the insolation, like the amount of watts per meter squared present on the spacecraft. And also where the sun is in the sky. So the results for power generation is the minimum average power generated is 4.43 watts, while the spacecraft maximum required is 4.9 watts. So the margin between what we have versus what we need is 9% for typical. So that's nominal operation with a very small payload duty cycle. And then for sustained safe mode, we have a 5% margin. This is our proposed implementation for solar arrays. For the sake of time, I'm not going to talk about this, but basically our goal here is just to make sure that the solar arrays are connected via low thermal impedance to the structure to reduce the peak temperature of the solar arrays and to kind of stabilize the temperature of the chassis and the internals. I'm not going to talk much more about this. This is kind of just a discussion point for the actual PDR. For a presentation, I will most likely just ramble about this for way too long, so I'm gonna skip it for now. So the summary of our power source is we don't need deployable solar arrays. We have, with a 20% margin on our loads, we have a 9% margin on our average power generated, but we also can't reduce the cell count, so we can't really save any money, which was expected, but we don't need deployable solar arrays. And the fun fact is that we're power budgeting for the worst case, which means that our average and maximum margin are quite a bit larger, which means most of the time we'll have a nice healthy margin. So let's select and size our energy storage. So the top level requirement for this is 5 watt hours capacity and 5 watt hours discharge current. That's with 4 times safety rating on the capacity and 1.5 times safety factor on the discharge current. So this is not hard to meet. Our battery capacity is extremely small. Additional requirements, obviously we need to be safe. We need to not pose a risk to human safety. So we need to have overcurrent and short circuit and over voltage and under voltage protection. Well, under voltage doesn't pose a risk to human safety. Under voltage just poses a risk to the performance of the spacecraft, but over voltage and overcurrent in particular pose a risk to human safety. So we need to make sure that we're protected from that. We'd also like to report the battery state of charge so we have a better idea of how the power system is performing while it's in space. So, you know, we can get some flight heritage out of this thing and be confident that it works. And we need to fit it to PC 104 standards and operate over negative 10 to 40 degrees Celsius. So battery usage for a 5 watt hour battery is as shown. APG margin is, you know, well, not but APG margins on the bottom there, just to kind of line up the minimum state of charge of the battery to the APG margin. And as expected, when we have a very large margin, we have a higher minimum state of charge on the battery. So everything checks out there. Implementation considerations. I'm going to skim over this really quick as well. This is more of a discussion point with the CSA at the actual PDR presentation, but for the most part, we're looking at doing a single battery pack with multiple cells. So we're using multiple unprotected cells, assembling together in a battery pack, and then we're protecting the battery pack as a whole. The only concern with this is that A, is this what we're expected to do when we're making battery packs? And B, is there any concern in the protection IC being a single point of failure? If so, then we have this solution, which is the dual pack design, where we split the pack where we split the one pack into 2 packs, each with its own protection circuit, to reduce to reduce that point of failure. The disadvantage of this is it makes it less efficient to charge and discharge the packs, because now you need diodes to prevent eddy currents from going between the packs, and you've added more components overall. So more components, does that equal a more reliable system overall? Typically no. Simpler is usually more reliable. So that's why we're not using the solution. This is our number one solution, is a single battery pack with multiple cells, most likely in parallel, but we could do a series configuration. It depends on the cell chemistry and how the system shapes up and what ends up being the solution. But for the most part, this is what we're looking at implementing. For cells, kind of the same thing. We don't have any strict requirements about cell choice. Basically what we're focused on here is just availability and which cells are the easiest to design with. So step 4 is power distribution. So top level requirements here is we have to supply 3.3 volts and our converter efficiency has to be greater than 80%. And that's up by the power budget itself. We'd also like to supply the main power bus rail to each subsystem, and I'll talk about that in a second. And we like to make sure that a fault in the EPS does not cause a failure of a subsystem. We like to make sure that a subsystem fault does not cause a failure of another subsystem. So if something happens, like you know, the comm system, say, consumes a whole bunch of power, it latches up and consumes a whole bunch of power, that doesn't cause failure to the satellite by causing failure to other subsystems. We can basically isolate that individual fault and correct for it. And we like to be able to turn on or off loads, aka subsystems, to reduce standby power draw. So if you notice in our power budget, when loads are considered off, it consumes 0 watts of power. Everyone knows in electronics that's not true. Standby current draw is a thing, but we like to reduce that as much as possible by actually like cutting power via an electronic switch to the loads, so they truly consume 0 watts of power, aka we're talking microwatts of power. They're not like the microcontroller itself isn't in standby mode where it ends up consuming, you know, a few microwatts or a few milliwatts, and there's, you know, pull-up resistors and that kind of thing, which are static loads that consume power, which adds up to a very large standby power draw. We're actually just killing power to the loads, so the only thing that consumes power is the switch itself, which is in the microwatt range, and we can effectively ignore that power consumption. And then of course we'd like to be able to report power consumption of each load for telemetry. So this is our converter topology that we're looking at implementing. Basically what's happening here is we're looking at a single centralized 3.3 volt converter, and we're looking at decentralized point of load converters for application specific loads. And these point of load converters are powered off of the unregulated main power bus voltage. And each subsystem has a separate switch for the 3.3 volt, and the separate switch for the main power bus. And these switches are known as power distribution management units because they're a bit more complicated than switches, but effectively they're switches. And the only subsystem that doesn't have switches is the onboard computer. Well, it does have switches, but the switches are always enabled. So even the EPS telemetry, you can turn off power to the EPS telemetry. You can turn off power to the payload, to the ADCS, to the comms, whatever, but you can never turn off power to the onboard computer. The onboard computer is always on. So about the switches and the fault protection, it's a current limiting switch, which is basically just an E-fuse. So it's an electronic fuse. It's measuring the current through the device. If the current exceeds a certain threshold, it opens the circuit up. It also has overvoltage protection and whatnot. And then in series with that fuse, we have an actual fuse, which is derated even more than the E-fuse. So if the E-fuse itself fails, the physical fuse will catch it. Power regulation and control. So top level requirements for this guy is basically just the energy transfer between the solar array into the batteries has to be greater than 80%. That is determined by our power budget. We have to meet NanoRacks requirements in terms of the deployment mechanism of the spacecraft, and we need a heartbeat signal from the onboard computer to keep the EPS alive. And so I'm just going to take a second to talk about this. So what the heartbeat signal is it's basically a clock signal from the EPS that prevents a watchdog timer on the EPS from resetting itself. What happens here is, or the reason why we're doing it is because it's a simple feature to implement onto the EPS, and it can correct for potentially catastrophic faults. So if the EPS, like power distribution or something like that, itself latches up or is an intolerance, or something happens to a subsystem that the fault protection isn't able to correct for, the EPS can basically die and, or so I should categorize more here. Either a fault happens, then the catch for that fault is the protection circuit will open and basically kill power to that fault, or the spacecraft will brown out to that fault, preventing or causing the OBC to die, preventing that EPS signal, the EPS from receiving the heartbeat signal. So either the protection circuit opens, killing power to the spacecraft, or the OBC browns out and dies, and that can be caused by the protection circuit itself or indirectly by another subsystem consuming all the power. Either way, if the OBC ever dies, the EPS basically resets completely, or hopefully clearing the fault and continuing on as normal. So it's kind of like a master watchdog for the whole satellite. So back to the first requirement, which we identify, which is the energy transfer efficiency has to be greater than 80%. The first question is, okay, well, we're going to use direct energy transfer peak power tracking. The answer to this is we're most likely going to use peak power tracking. DET, we've done a bunch of analysis on it, and we think we could make DET work, but we know we can make peak power tracking work. So we're just going to use that because it's more flexible. And for regulated versus quasi-regulated versus unregulated bus, our subsystems are happy having the unregulated bus given to them for their application-specific point load converters. They don't need a highly regulated bus. They only need the 3.3 volt like rail. So implementing a regulated bus or quasi-regulated bus in this situation is not super important. We're only having 1 year mission life, so we don't need dedicated battery chargers, or we're trying to charge the battery in a very specific way. So in this case, an unregulated bus is going to work just fine, and it's the most efficient solution. So implementation consideration for power control. So what we're doing here is, I'll go back to this slide. So as you can see, we have the NanoRacks required switches on the power system to prevent the spacecraft from turning on after it's deployed for 30 minutes. So we have a low side switch and we have 2 high side switches there. So D1, D2 are high side, D3 is low side. These switches are electronic switches, meaning that they're basically MOSFETs. If you go back to this, they're basically these. They're back-to-back MOSFETs with a controller. Some of them are just single MOSFETs, but they're MOSFETs and a controller are what these switches are in this diagram. And the enable signal for these switches comes from somewhere. And where that comes from is this diagram here. So these switches here, these red switches, these are physical mechanical switches. These are the deployment switches, which are located on the ends of the spacecraft rails. And when the spacecraft is deployed out of the deployer, these deployment switches close. So D1, D2, and D3 all close, and the RBF switch is closed when the pin is removed. So when the spacecraft is deployed or is removed from the deployer, the coin cell battery is then immediately connected to the 30-minute timer. The 30-minute timer basically turns on and it starts a 30-minute timer. During the 30-minute period, the enable signal remains low, meaning nothing else in the spacecraft is turned on. You literally have a coin cell powering a 30-minute timer. If at any point in time in that 30 minutes, D1, D2, D3, or the RBF switch open and then close, the 30-minute timer is reset. Only after 30 minutes continuous of D1, D2, D3, and the RBF being closed does the enable signal from the 30-minute timer go high. When the enable signal from the 30-minute timer goes high, we'll go back to this diagram. You will see here, I'll use my mouse for this just to kind of point. The enable signal is this signal right here. So each deployment switch has enable signal to it. So D2, when it gets enable signal, it immediately closes. D1, when it gets enable signal, it basically is ORed to the primary power. So in this case, enable signal, the primary power is not on because this switch hasn't closed. So the enable signal turns on, and then the AND gate checks to see, okay, well, is the battery voltage high enough to actually turn on? The under voltage lockout is very ambitious, or not, it's very conservative is the word I'm looking for here. So it's not going to, like, not turn on because the battery voltage is, like, not ideal. It's not going to turn on to protect the battery in addition to the protection of the battery circuit. But anyway, it checks the under voltage lockout, and if both the enable signal and the under voltage lockout are okay, it turns D1 on. So now primary power has officially turned on. So now this switch is latched to primary power, meaning that if the enable signal goes away, aka the timer resets, the power system is latched on. But remember, if you reset the timer before 30-minute timer expires, the enable signal does not go high. So once the satellite has deployed, it doesn't matter if that timer dies or whatever, the spacecraft stays on. And same with the low side. So once the primary power turns on, it essentially latches the low side switch on. Yep. Yep, that's what I was going to say. And the thing to note here is that with the charge switch, if you plug a charger into the EPS system, it has a charge signal which only turns on the EPS, it only turns on the low side switch. So you're able to charge the battery, but you aren't able to power any of the power distribution management or the EPS telemetry or any of the loads. You're just able to charge the battery. If we go back to this diagram, this is what the watchdog is. So once the 30-minute timer has expired and the enable signal goes high, this enables a watchdog, which then starts looking for the heartbeat signal from the onboard computer. If it receives a heartbeat signal, it is happy and it just stays here. If it doesn't receive a heartbeat signal, it resets the 30-minute timer. The enable goes low, killing the watchdog, and the 30-minute timer basically then counts down from 30 minutes again. Now, if you go back to this diagram, when this situation happens, only D2 closes. So D2 closes, killing power distribution management, killing the loads, killing everything else in the spacecraft, but the batteries are still able to charge. That's the really important thing, is the batteries are still able to charge. So during that 30-minute period, if it's in full sun and that heartbeat signal goes away, the batteries can still charge, which is really good. And if at any point in time the battery voltage drops too low, the end of voltage lockout will kick in and it'll actually kill D1, killing power distribution management, killing the loads as well. Just kind of like a hard brownout. So if you use too much battery, the battery voltage drops too low, it'll kill the satellite as well. EPS integration. So right now we're designing for a PC104 template and we only need 20 millimeters off the battery pack. That's pretty much all we have to talk about there. For electrical interfaces, the EPS will provide a regulated and protected 3.3 volt rail. It'll provide an unregulated main power bus rail. and it will provide or it needs enable and disable inputs, or so the onboard computer can control what loads you turn on and off. It'll have a single I2C bus that all of the health telemetry will be accessed from, and it requires a 1 hertz heartbeat signal immediately after boot to remain alive from the onboard computer. So development and test. So the test plan, the focus for preliminary design was basically just to verify unknowns in subsystem requirements, and this was done by developing proof of concept prototypes and testing them. For critical design, we're going to test all of the implementations, so every single thing, not just where we think is critical. We're going to build complete implementations of everything and test those individually, and then we're going to basically build a full engineering prototype and test that as a fully integrated EPS, and that's more flight quality testing. So all of the testing up until that point is just functional. Does it work? Does it not work? Once we get to the fully integrated EPS, that's where we start doing things like testing for flight. So we're testing thresholds of performance and testing to make sure all the requirements work and all that fun stuff. So what we've done so far. So in preliminary design phase, we've built a bunch of proof of concept prototypes and we've tested a bunch of them. So each kind of block of the EPS, we've had requirements that we'd like to verify. So for power generation, the one requirement we'd like to verify is the peak power tracking and making sure that we can actually meet the 80% efficiency for peak power tracking. We had 3 different implementations. So we built 3 different boards to test that, and we haven't actually tested it yet. So we don't really have any conclusion. Energy storage, once for this guy, we wanted to make sure that we could test protection in the low side inhibit. We tested it, and it works exactly as inspected. We're very confident that we can meet the nanox battery requirements for this. For power regulation and control, that circuit diagram about how the deployment sequence works and all that fun stuff, that is a very difficult, well, not difficult, it's very complicated. There's lots of edge cases where that might cause you problems. So we wanted to make sure that that actually worked properly and that it did meet nanox requirements. So we built it and we tested it, and as far as we can tell, it does meet nanox requirements. So we're pretty happy with that, and we don't need to do any more development and try to make sure that those requirements can get verified. For power distribution and management, we wanted to make sure that we could test our voltage regulator performance. So when we said that we have 80% efficiency for the 3.3 volt converter, and we have like noise and ripple requirements, that we can actually meet those, as well as we can properly protect the converter. So how well does this E-fuse actually work? So we built that thing and we more or less tested it. We weren't able to do really extensive testing on it due to some bugs on the on the board, but we have worked that out and we'll do more extensive testing later on. So what we have to do before PDR, we have to update our documentation to reflect our requirements. We have to discuss this documentation with other teams and make sure everyone's on the same page, and then really set these requirements in stone to move forwards. And we have to finish getting our MPPT test data, or PTT, peak power tracking test data, and get our fault protection test data before PDR. And that's it. That's the end. So thank you for watching the presentation. Yeah, please give me feedback. This presentation was brought to you by Canadian Space Agency, National Research Council Canada, Rainhouse Canada, SolidWorks, SSL, Altium, and Rocket Lab. Thanks for watching.